My name is Roger Palmer, and I'm a member of the Royal Victoria Yacht Club in British Columbia. RVYC is an active racing club, and one of the many fleets is the Mini 12 fleet. The fleet races every Saturday and usually has a lunchtime speaker before racing starts. In 2015, I gave a series of lunchtime lectures on sailboat racing, including the theory of sailing, sail trim, tactics, and rules. This series of videos will cover the same material which was presented in these lunchtime talks. The syllabus for this series of lectures is sailing theory, sail trim, wind direction and shifts, tactics, and rules, all with the objective of winning sailboat races. Winning sailboat races is a combination of three factors: going the right way, knowing the rules, and going fast. Going fast is not a simple topic. You want to maximize boat speed in the desired direction, and you want to use the available wind conditions. So, what makes a sailboat go? For that, we're going to have to look at the physics of sailing. To start out, consider a curling stone that is already moving on a sheet of absolutely frictionless ice. It will keep going forever in the same direction if the friction is zero, unless some other force acts on it. To understand these other forces, we're going to have to go back to concepts which were taught to you in high school. Recall that force is equal to the mass times the acceleration. You can rearrange these terms so that acceleration is equal to the force divided by the mass. Looking at this relationship, an object of mass m is accelerated proportional to the amount of force F that is applied. Heavier items with larger m require more force to give the same acceleration. Wind is the movement of a mass of air on a continuous basis. We often think of air as having no mass. However, that's not the case. Think of the area of a Mini 12 sailing rig. The amount of air that interacts with that rig in a 10-knot wind is equal to 150 pounds of air per second. Our curling stone, which is gliding across the ice, has a momentum equal to its mass times the velocity. Wind has momentum also, and sailing is all about changing the momentum of the wind. This concept is a non-traditional way of describing what makes a sailboat go, but if you keep this in mind, that this is all about changing the momentum of the wind, the following explanations will become much easier. Another concept you probably remember from high school is that for every action, there's an equal and opposite reaction. If you push against a wall with a force F, the wall doesn't move, and it feels as though it's pushing back at you with the identical force F. In these discussions, we must remember that force, velocity, and acceleration are vectors, and vectors have magnitude and a direction. Vectors are represented on diagrams by arrows, where the length of the arrow represents the magnitude of the vector and the orientation represents the direction. Vectors which are at an arbitrary angle can be broken down into their x and y components. This is called resolving the vector. Multiple vectors of the same type can be combined by starting one vector at the pointy end of the previous vector. As an example, consider a flatbed truck traveling due south down a highway at 60 miles per hour. You are standing on the flatbed and you start to run north at 10 miles per hour. The net effect of these two velocity vectors is that you are actually traveling south at 50 miles per hour because your arrow is in the opposite direction of the truck's arrow. As another example, consider that the truck's bed is quite wide. You're standing off on one side of it, and you start to run due east at 10 miles per hour. Now, we can look at this diagram and understand what's going on. The black arrow represents the addition of the two vectors, the initial vector being the truck's velocity, the blue vector being your velocity, and now the black arrow represents your velocity with respect to the ground, and it is approximately 61 miles per hour in an angle slightly east of south. Now we're going to consider a boat just sitting in the water, absolutely stationary, no wind, no current. In order for this boat to move, some type of force is going to be required. So let's apply the force by trying to tow the boat. And we're going to use a gauge which will show the force F that is required to move it. The boat will accelerate depending on its mass and the magnitude of the applied force. And it's going to continue accelerating until the drag is equal to the applied force. We'll do an experiment and plot the results. This sort of testing is usually done in a towing tank, where a model, or a small vessel such as a Mini 12, is towed at a given speed, and then the force is measured. At lower speed, the force required increases linearly with the speed, and this continues up to a certain point. Beyond a certain speed, the amount of force required to maintain that speed increases remarkably. In all cases, we can say that drag increases with speed, and the boat will continue to accelerate until the drag equals the driving force. Now, drag has two components. The first is friction, because it's moving through a viscous fluid, and then the second part is wave making. Once a vessel is going at what is called the hull speed, additional force or power that is added primarily goes into creating bigger waves. The boat is going faster, but a lot more energy is being used because of the waves that are absorbing the energy. In order to go faster than hull speed, a vessel needs a lot more power or needs to climb out of the water by planing or riding on foils. The actual hull speed in knots is approximately equal to 1.3 times the square root of the waterline length in feet. In all cases, the driving force for making the boat go is the interaction of the sails with the wind, such that the wind's momentum is changed. We'll now study the interaction of the sails and the wind on 3 different points of sailing. We'll start out with an easy case, going downwind. Now, our boat only has a mainsail for this discussion, and the wind is coming down from the top of the screen. Some of the wind is not affected by the boat, but the wind that goes near the sail gets diverted and slowed. So you can say that the sail is slowing the air mass. In other words, the air mass is being decelerated, which means that the wind's momentum is being changed. A force is causing this deceleration, and a reaction to this force is what is driving the boat forward. We can show this interaction in the form of vectors. Here is the original wind vector. Then this is the wind vector after it interacts with the sail. So there's a net acceleration vector caused by the sail. You'll notice it's in the opposite direction of the original wind. A reaction to this net acceleration vector is what is the force that is pushing on the sail and pushing the boat forward. By projecting as much sail area as possible, you'll end up with the highest driving force. Next, we'll consider reaching. Again, the wind is coming down from the top of the screen. The sail is diverting it at this angle. So you can see that the original wind vector has been bent due to the acceleration caused by the sail. Now remember the F equals ma relationship we saw earlier. That means that there is a force causing this acceleration. The reaction to this force is the force that's heading the sail, and we'll examine this in some more detail. This vector can be broken down into two components: a force in line with the boat centerline. This is a good force for us because it's pushing the boat along in the direction we wish to go, and a force at right angles to the boat centerline. This is not contributing to our forward progress. What it is contributing to is a leeway. Now we need to consider the effect of the keel underneath the boat. This is a cross-section of a keel, and the red arrows represent the water flow coming from the left side of the screen going toward the right. The keel acts somewhat like the wing on an aircraft or the sail of a sailboat. It will be at an angle, a small angle to the flow of the water, and by being at that angle, it deflects the water, thereby creating two vectors which are known as lift and drag. Here is a plot showing what happens at different angles of attack. The blue line equals the lift force. You can see that it increases as the angle of attack increases up to a certain point, and then it starts to come down. The red line is equal to the drag, or the friction and the induced drag, which is holding the boat back, and it increases continuously as the angle of attack is increased. The angle of attack of the keel is caused by the lateral force of the sail in combination with the water speed, so that the keel's lift is equal to the lateral force. The angle of attack is the leeway, and higher water speeds result in less leeway. This diagram completes the picture. You'll note that the boat's track, as shown in the red arrow, is not equal to the heading. There's a bit of a difference, and that difference is the leeway angle, also known as the angle of attack of the keel, such that the lift generated by the keel is sufficient to compensate for the lateral force reacting on the sail. Both the keel and the rudder have similar curvature on both sides, but in opposite directions. That means that they are symmetric hydrofoils. Sails are different. They're asymmetric airfoils. Now we're ready to tackle sailing to windward, otherwise known as beating. This is the hardest one for most people to understand. How can a boat being propelled by wind possibly sail generally toward the wind, is the question we're always asked. Well, let's look at the vectors and we'll figure it out. Here the wind is coming at about 45 degrees to the direction of the boat. As the wind interacts with the sails, it is being deflected. So the wind's momentum is being changed. And it's being changed because the wind is being accelerated in the direction shown by the yellow arrow. It's the sail that's doing it. Reaction to the force that's involved in that acceleration, the so-called reaction force, is shown here in red. And this is the force that is on the sail. And we'll examine that vector and break it into two components. The red small arrow indicates the forward driving force, which is driving the boat forward, whereas the sideways force is shown in white. This is the lateral force which we're relying on the keel to compensate for. If the helmsman steers the boat too close to the wind, a phenomenon commonly known as pinching, the driving force, the red arrow, becomes much smaller, whereas the sideways force, the white arrow, remains about the same. So what happens in the extreme is the boat is going as fast sideways as it's going forwards. A crew often adjusts sails to be much closer to the center line than optimum. This is called being strapped, and the idea is that they believe the boat can sail closer to the wind in that configuration. Unfortunately, when you look at the vectors, you'll realize that the forward driving force becomes much smaller and the attempt fails. So in general, when in doubt, let it out. To complete our first lecture, we need to remember that there's also windage. Not all the wind is helping you. It's causing parasitic drag, as it hits the mast, the rigging, the hull, the crew, the dinghy, whatever. And it's causing a drag vector in the direction of the wind. It is not helping him go quickly in the direction you wish to. Okay, this is the end of the first video on sailing theory. Now we're through the basics, we can get into some more serious stuff. So the next video will focus on sail trim, trimming for speed.